Okay, we'll go ahead and get started. First, to set some expectations for this presentation of the webinar, we are talking at a high level about GlobalPlatform and a trusted execution environment. This is meant to be an introduction to the TEE and some of its APIs. The main purpose here is to give a broad understanding of what TEE is and how it works in some type of device. This is not going down into some of the specific details on a implementation. There is a Sequitur Labs webinar coming up that will go into some specifics on deploying with a development tool. So today, our first agenda item is a quick introduction to GlobalPlatform. For those of you who may not know who we are, GlobalPlatform is an industry standards organization. We've been around since 1999. Our first set of specs were for payment cards or ID cards, mobile money kind of situation. The idea is making a very comprehensive standard, secure standard for working with credit cards. We moved into the secure chip technology very quickly. For those of you that have a small chip on your credit card, that's thanks to us. We moved into that technology through about 2007. We concentrated on the secure chips for the credit cards, for IDs, and for other government type entities, and major enterprises. From 2007, 2015, roughly, we introduced the idea of moving the credentials to devices. Many of you may have, if you have an Apple iPhone 6 or later with Apple Pay, you're using GlobalPlatform specs. It is also in many of the Android devices. So if you're using a payment wallet from Android, you're probably using part of our specifications as well. Our specifications have used to secure the payment credentials at this point. That's the main purpose, or the main use, I should say, of the GlobalPlatform specs. From 2015 on, little more than a year ago, we started looking at the future of the secure chip type technologies. What do we need when we go out to the rest of the market? And IoT and wearables is becoming the focus of where we're heading to. So the mission of GlobalPlatform is to create a standard. We are a nonprofit, cross-industry, international association. We have several different organizations or several different groups. Depending on the groups are spread across device, a card, and a system specification. So the idea is that we have each particular domain or group is focused on a particular specification. The device group is where the trusted execution environment originates. This group also writes specifications of how to access a secure element from within an operating system of a device. The secure element is that chip you have on your credit card or something similar. It is a resistant or tamper-resistant media that protects all of its credentials. And the system specs are there to communicate between service providers, controlling authorities, trusted service managers, and so forth that are out in the internet that want to be able to reach down into your device to give you a new credit card or other type of system, other type of application. So the secure element, as I said before, is a tamper-resistant platform capable of securely holding your credentials. So far from 2013, 2015, we roughly have, there's been roughly 17 billion GlobalPlatform secure elements produced. So these are in a form, either a card or in a individual secure element that is then started into a device or other media. So when we talk about specifications in general, the main purpose of a specification is to make the new ecosystem first to be interoperable. Anybody in that makes a device or a product go into our specifications, do so in a way that becomes interoperable to other applications, other systems based on the same specification. It also offers flexibility. Our specifications do a multi-application environment so that a secure element or a trust execution environment can run several apps simultaneously. And the main part that we strive to do is offer security, ways to make sure that the credentials that are loaded into the systems are secure. So the specifications we have it's not an all for nothing proposition. They're used in various manners, in various modes. I mentioned at the beginning Apple Pay and Android implementations. Many of those use part of our specification in order to open up their ecosystem to competition, to allow for multiple chip dividers or multiple application providers to provide solutions for their platform. As I said before, interoperability is one of the biggest aspects of a standardized product. There's also, though, ability to work with many different business partners. I'm able to switch between one vendor and another that are both compliant to a specification. So it reduces the development time, the testing time, the cost. It's faster market. Because it is built on a specification, it basically future-proofs the investment we're making. So as a quick introduction to GlobalPlatform, our mission, our purpose. So we're going to go into now, shift gears into the trusted execution environment architecture. The first thing is to understand that the trusted execution environment starts from a secure boot, so that when a new environment starts up, that it is based on a root of trust. Now, this is a very simplistic view of a PCB. It shows a system on a chip with its internal resources. That would be some type of key as well. There's also ability to do a off SoC security processor. The Secretary Labs will talk a little bit about what's called Trust Zone, which is a system that offers a secure boot for the TE environment. So on the boot process, the GlobalPlatform standards are only apply after the system is booted. So the way the system boots into a secure environment is up to the vendor. We do have some requirements on that boot process. One of those being that has a root of trust. A root of trust meaning that there is a key that is secured that cannot be modified without the proper security, proper permissions. Normally, we boot based on some kind of ROM code. Now, this is the point says there's other approaches exist. The Trust Zone is one of those that boots from a ROM-based code to verify that when it's loaded correctly. So normally, a TE boots first. There's a term here, REE, and I'll get into that in a few minutes, what the initials mean. And the system may support a boot time TE. Now, often there's it's a subset of a full TE. So something that is outside the full specification of GlobalPlatform, but again, we're able to have a sub TE type system boot as well. So I talked about the REE for a moment. The rich execution environment is called, and that is your normal operating system, your normal device system. So you have to think of it as a rich OS, whether it be Android or Apple or God forbid Windows. A rich OS that boots, that then has various applications that are loaded into that OS. So the basic definition of a smartphone, loading in multiple applications into the OS to supply some service or some feature to the user. Unfortunately, there is the strict possibility of a virus or some kind of other malware being loaded into the system. And they're very easy to get into the OS itself. Rootkit is a primary name of these types of malware. So the idea behind the trusted execution environment is to set up another environment side by side with a rich OS. The idea is that it starts from the hardware platform up. So it provides the way to securely boot into the OS or into the TEE without having the root of it exposed to a malware or other system. So we have a trusted core framework as a start of the TEE specifications that defines how the system is, or after it is booted, what is offered to the applications. We have trusted drivers that are outside the specifications, but they're drivers that are built into the TEE that we know that we can trust, that then provide us the services. These services are the key storage, trusted user interface for keyboards and screens, access to a secure element, or other hardware resources. And then we have the TEE communications agent. That is the main thing we'll be talking about, part of that today. And on top of that is GlobalPlatform published APIs in which the applications then invoke. So there is an idea of the rich applications talking to the trusted applications through a communications agent. And we have several different, or because it's a rich operating or trusted execution environment, we have different applications called trusted applications that can run in the environment. When a malware shows up and attempts to talk to the TEE, it is checked and discarded if it doesn't have the proper permissions to get into the trusted execution environment. A little better architecture showing some of the APIs that we have. There is the first one on the left side of the screen, the REE. We have the idea of a TEE protocol communicating to a TEE client API. The protocols provide the ways of securing communications and authenticating the application through the client into the TEE. The message flows are from the rich environment communication agent, the TEE communication agent. The TEE communication agent does a thorough check to make sure the message coming in is properly authenticated and encrypted before it moves up to the rest of the service. So give an example in a little idea here. We have a message that is started in a client application that is then properly formed and sent to the client, to the TEE client API, moves through the rich or to the REE communications agent, through to the TEE communications agent where it's checked, through the internal core API, and finally to the trusted application. That trusted application can then send another message if it desires to another trusted application through the internal core APIs. Allow for that communication between trusted apps to to take place. The trusted app can then send its response back through the APIs, and the trusted application can then send its response back through the channels back up to the client application. So that is a very quick introduction to the architecture. So we have about 30 minutes to go through the rest of the APIs, and I'll walk through these. I'll try to cover these at a way that we can, I should say the main APIs, walk through these in a way that makes sense, and to give you an overview of how a TEE system is implemented from the ground up. The first is that there's a number of specifications that define the TEE. We'll be looking at the first, or these two, the device TEE, in other words, the TEE client API, which allows for the rich applications to communicate to the TEE. And the second is the TEE internal core API. So these two specifications define how these, the basics for a TEE. These are also the two APIs that are required for the minimal support. There are a number of other APIs available: accessing a secure element, the TEE sockets, ability to communicate to an external server, or network-based server, a trusted user interface to allow for user entry in a secure system, and a debug specification. The debug specification allows a developer to look at what their application is doing, why is it causing, or what is the issue with the application, to capture some of its feedback or its issues, its errors. There is also a TEE protection profile. We will not go into this, but the protection profile exists in order to provide a way for us to make sure the trusted execution environment is protected. The protection profile details how the TEE communicates to any outside entity and how it protects those ports. And it is reviewed by an external agency to make sure it is complete and that every protection is valid. There is also a compliance test suite that allows for a TEE implementation. Secretary Labs is using the OpT system that has been tested through the test suite to ensure that it is a TEE compliant configuration. So a little bit different architecture picture, but the same overall idea. We have the hardware layer and the rich OS on the left side with its various applications, and the hardware layer and trusted execution environment on the right side with its core API, its different applications, and also additional APIs available. Also, the client API is in part of the rich execution environment to provide that communications. So basically, when an application wants to talk to its TEE counterpart, it first has a context to make sure there is a TEE that is existing on that device. If it has the proper context that there is a TEE access, it gets that context and able to move on. With that context, it's able to open a session to the particular trusted app. Every trusted app is identified by UOID. We'll get into that in a moment. And then after the session with that, between the rich application and the trusted application is established, they can then start exchanging commands back and forth. It is highly encouraged that these commands are encrypted as they are going back and forth between the two systems. The trusted application, every application must have a series of functions that are exposed. So when you're writing your trusted app, remember that you have these interfaces that are required. So there is the create entry point, destroy entry point, open session entry point, close session entry point, and invoke command entry point. So each one of these are labeled here. More information is in the specs. And I know that the Sequoia Labs development tool also does a good job of working with these for developing your application. The trusted application has several configurations. We talked a little bit a second ago about UUID. So that configuration is set through the property, the GDP or gpd.ta.appid. There are several other configurations. One is whether an app can be was only a single instance or a multiple instance of that app. So there is a true set to each one of those properties. There's instance keep alive. There is a instance for a property for data size. In other words, the maximum size information coming into the application. So again, as we go through these, remember the point here of the trusted execution environment is to provide security. So we are looking at the data size and the stack size as they're coming into the trusted app in case there is a malware that is attempting to overload one of the applications. We can set a size to make sure that there is not a stack overflow or there is not a memory run-on or a pointer error. You can also set the version number for the application and a description for the application. Now, the trusted applications can also get information from the system itself. So we can ask for the client identity to make sure that what is talking to it, it recognizes. It can also ask for the device ID and for the API version of the TE it's running in. And it's also can ask about the current, about itself as is the current TA. So TAs will have a property or have a function called TAE panic. Once a panic is thrown, the TAE must destroy all resources opened, or must destroy the TA instance and reclaim all the resources. So one other note here is that when the TAE panic function is retrieved, the TAE or the trusted app does not send any more information out to the rich environment. We do not, if a TAE panic occurs, we do not want to give any kind of hacker a instance or an idea of what caused the panic. There's ability for the trusted app to have its own storage. In the current specifications, it defines a single trusted storage space. There is a new version of the specs coming out, and it may actually be out that allows for a multiple or having multiple storage spaces available. However, I do not know if opt supports the single or the multiple, so it's always good to go to make sure that to make sure you support what is known, which is of course the single trusted storage space. The trusted storage space is used to store whatever you need for your application, whether it be keys, key pairs, some kind of data object, and so forth. So this is a persistent storage that can be used or can be accessed by other applications. There is also the idea of a rollback, meaning that if there is something that is entered into the storage that attempts to do a rollback attack, that it can be detected and dealt with. There is the idea on the end of that rollback detection is the property called protection level. The protection level is the confidence you have in the data you're receiving. So if you're receiving something from the rich execution environment, the typical protection level is up to 100, meaning that, okay, don't trust it, make sure and check it, make sure everything's right on it before you actually allow it to do anything. Up to 1,000, which is, yes, coming from hardware assets that are controlled by the TEE or by something I extremely trust. So I don't have to check it as much. So make sure as you write your trusted applications to take into account an idea of protection level. Where is the data coming from, and can I protect it? I mean, can I trust it or not? There are also transient objects. So these have no identifier. The idea is to be able to store something for a short time. When the TA instance is destroyed, all the memory for the transient object is reclaimed. Some of the APIs available for the persistent and transient objects are as shown below. The create a persistent, open a persistent, rename a persistent, close and delete, and allegate transient. So one of the notes here is that a transient object having no identifier is not accessible from another TA. Since the persistent does have its own identifier, it can be accessed from another TA that knows the identifier. However, a transient object is meant to work with that one TA and nothing more. Part of the default APIs is also the crypto API. So different operations are available to be, or different algorithms are able to be used. The specs define exactly which algorithm can be used, and you can make your own if you desire. We'll get into how you make your own in a moment. There is the idea that you have several different types of message functions: the message digest, symmetric and asymmetric ciphers and keys, and encryption systems, MAC functions, key derivations, the random generator function. So these are built into the API. There's also the idea of a time API. The time API allows for basically to capture the time that you are looking for your TA. So there's three types of here. One is the TA time itself. This is a property that you set for your TA. If it is a time you set for the TA and your reboot occurs, one of the items is it must be able to exist across the reboots. There's also the system time. Basically, the TE is able to get the system time and give it to a TA instance, so it knows what the system time for that device. There is also the idea of the real or rich execution time. So a time that rich execution environment thinks it is. And these can be sent, these functions can be gathered by the TA. There is a small example of a TE gathering some local time, making sure that the local times are not out of whack, as in making sure that if you wait and get system time 2 times, that the second one is greater than the first one. And finally, the Arithmetic API. So the Arithmetic API allows for you to basically, just as it sounds, to be able to perform arithmetic operations. It is made for being able to allow you to make your own crypto functions. However, it also has the ability to do other mathematical formulas. There is the idea of a size limit. The size limit is variant on the implementation. So if you retrieve, you can retrieve the property of the size limit by asking the system what does it support. From that, you know what size of number you can deal with. So this went quicker than expected. This is my last slide. I was expecting to go through these a little bit slower than I have. I'm hoping that the information I was able to give gave a good light on the different applications. In the summary, though, there is the main APIs, the client API and the core API, that are needed to implement a basic TE system. There are many other APIs available to us, the Sockets API, the SecureLink API, the TUI API, and so forth, that allows for multiple additional functionality for each of your trusted apps.